In this lecture, we're going to discuss how the homology groups are computed. So as a very quick reminder, what we did is we defined something that was called topological homology. And this is when we start with a topological space. And the drawback with this kind of approach is that it's impossible to compute from what we call first principles. So just following the definitions. The reason for this is because the way you define homology, so this is just a very quick review. Let's say you want to find the nth homology group of a space. The way you do that is you first consider all chains, n-dimensional chains in X. You have a boundary map into n-1 chains, and then you have n+1 chains mapping n+1 chains into X. And the way you get the homology group is if we call this, let's say, delta n, and we call this delta n+1, then the way you get the homology group is it's the kernel of delta n modded out by the image of delta n+1. And that quotient is what gives you the nth homology group. So this over here, this is what we call the cycles. That's the one that have no boundary. And then we would say that a cycle is homologically trivial if it can be increased in dimension. So you can find something of one dimension higher whose boundary will give you that cycle. So in other words, the cycle, the inside of the cycle can be filled in. And the reason why these are impossible to compute from first principles is because this group over here, this is the collection, you say the free abelian group, generated by all continuous maps from the n-dimensional, let's say from the n-dimensional geometric simplex into X. And there's an infinite number of such mappings. So because of this, it's just infeasible to even, it's an uncountable number. The advantage, of course, is it's topological. You can do this with any topological space. And then we saw another approach to homology where you do not start with a topological space. This is what we call simplicial homology. And this is when you start with a complex. This is a simplicial complex. And in the old days, what people would do is for a given complex, you can turn it into a topological space. So you can convert that into a topological space, which some people denote it with just like absolute values, and that's called the geometric realization. Now, the drawback with this combinatorial approach is, of course, different simplicial complexes might describe the same topological space, and not all topological spaces arise in such a process. So it's a very limited kind of approach. However, fortunately, so the good news is, so the advantage is that the nth homology group of a complex is what we say easy to compute. Now, when we say easy to compute, we mean there is a algorithmic procedure that will do it for us that does not require any clever type of arguments. The fundamental group is not easy to compute. If I give you a topological space, like for instance, if you want to find the topological, so let's say you want to find the fundamental group of the torus, you first have to recognize the torus as a quotient. And that's by no means obvious. Like it's by no means obvious how you realize a certain topological space as a quotient. So there is no, you can say, algorithmic method for computing fundamental groups. They're harder to find. These homology groups, they're easier to find. There's an algorithmic approach. You can put it on the computer and it will do it for you. But it's something that doing by hand can sometimes be tedious to do. But that's the advantage, that they are, quote, easy to compute. And let's discuss why it's easy to do this. So the reason for this is because when you're doing simplicial homology, it's sort of the same approach, but instead of considering, so it kind of goes the same way. You have n chains, n-1 chains, and then you have n+1 chains. And as before, you have the boundary maps. But the difference is that when you're talking about homology, topological homology, you're considering maps from the n simplex into K. And this will make absolutely no sense here. This is not a topological space. What does it mean to map that continuously? So the approach that we use in simplicial homology instead is this is, by definition, this is the free abelian group generated by all oriented n simplices in K. So what's an n simplex? Well, this is a different type of simplex. This is a combinatorial simplex. So an n simplex is just, it's an element of K whose cardinality is equal to n plus 1. Okay, so this is sort of a combinatorial simplex versus a, what you can call it, like a geometric simplex. So a combinatorial simplex will just, let's say, be a set of 3 letters, whereas a geometric simplex, you would write delta 2. And this is supposed to correspond to a 2-dimensional triangle. And because it's geometric, you include all of the points and everything, whereas a combinatorial simplex, that would just be 3 points, right? It's just 3. It's just a set of 3 points and nothing more. The intuition, of course, is that the 3 points can then be like embedded in some Euclidean space in an affine independently way so that they fill out a triangle. That's the idea. But when you're dealing with simplicial homology, you're not doing that. You're just focusing on the combinatorial aspect of this. So that's what we mean by an n simplex. And there's a finite number of them because a complex is just a finite set whose elements are sets themselves. So you just choose all subsets of K that have n plus 1 elements, and that's what forms the n chains. We make them oriented. So by oriented, it just means you basically just make it a word. So you would take these 3 letters and you put them in some kind of word, A, B, C. If you were to interchange them, then the convention, if you swap 2 of them, the convention is you just put a minus in front. So that's what we mean by an oriented simplex. So you first choose a simplex, and an orientation is just a word formed out of those letters and nothing more. And this is how this is defined. This is a free abelian group, but it has a finite number of generators because there's a finite number of simplices. So whatever this group is going to be isomorphic to z to some power. This one is going to be isomorphic to z to another power. Maybe I should actually do it like this. So all of them are going to be isomorphic to various copies of z, because these are just free abelian groups. And then the maps between them, in the context of linear algebra, you can just say that this is like matrix multiplication. And we did an example in the last lecture where we saw that when you try to compute the simplicial homology, it leads to essentially a linear algebra problem. I say essentially because it's not typically what you think of a linear algebra problem. This is not the real numbers, but it's sort of the same idea. And let's maybe discuss the following calculation. So computation of simplicial homology comes down to the following problem. Let's say you have a map from z to the a, z to the b, z to the c. This is given by some matrix, this is given by some matrix. And in order to find homology, you have to consider the kernel of b, and then you have to mod out by the image of a. And if you can calculate what this is, then you will have a method for finding homology. So I want to first focus on this b over here, because this is easier to work through. So the kernel of b would be the set of vectors in ZB, so that applying the matrix to that vector will give you 0. And of course, when we say 0, we mean the 0 vector in this group. So, but what is this? This is just what you call, what in linear algebra you call that the null space of B. The distinction, of course, would lie is that in linear algebra you usually talk about the real numbers, but it's the same idea. It's what you would call the null space. And the null space, this is going to be isomorphic to z to the d, where d, the dimension, this is just the dimension of the null space. So this is what you call the nullity. Perhaps you recall this, the nullity of B. And I'm sure you all know how to compute this. You would take your matrix, you would row reduce it, and then you would just count how many free variables you have, like how big is the subspace of vectors that get mapped to 0. So that's the way you would do it. So calculating the kernel of B is actually quite straightforward. It's not necessarily equal to all of ZB. It will be a subgroup, or maybe you can say a subspace. Technically, it's called a module, a submodule, but let's not make a big deal about that if you're not familiar with that. So it's just going to be isomorphic to that. And that's the way you find the D. But what do you do with the image? So let's discuss how one approaches the image. So to make it a little bit easier, so here's like a simplified problem. Let's say we're mapping Z to the A by a matrix, Z to the B, and let's just completely forget about the other one. So let's say it's not here, it's just that. And we want to compute, so instead of the kernel, just to make it a little bit easier, let's say we compute Z to the B mod the image of A. How do we determine what that is? If you're familiar with this, this is what they call the co-kernel of A. But if you've never seen it before, then do not worry about it. This is basically what we want to find. And to make it even easier, you're going to consider, let us assume that the matrix A is diagonal, that it's a diagonal matrix. This is very common, by the way, in linear algebra, that if you want to understand how something works, it's often a good idea to just assume that your matrix is in diagonal form. Try to solve the problem in diagonal form, and then see how you would solve it more generally. Often what happens is that if the matrix is not in diagonal form, you can often put it into diagonal form. That's what we call choosing a basis in linear algebra. So that's why we're, for the moment, we're assuming that A is in diagonal form. So for example, let's say we have Z to the 2 mapping into Z to the 3, and the matrix here, so this has to be a 3 by 2 matrix. Let's say it's the matrix, let's say it's 1, 0, 0, 2, 0, 0. So when we say a diagonal matrix, we mean diagonal in a more general sense. It's not necessarily a square, but things go down the main diagonal, but then you might have zeros at the bottom. So let's say that this is our matrix. And what we want to do is, well, let's say the vector here is x1, x2, then A applied to this vector would be 1, 0, 0, 2, 0, 0. And then, as we typically do, we write the vector into matrix form, and then we multiply this out. So this would be 1x1, 2x2, and then 0. So in the end, we end up getting 1, 1x1, 2x2, 0. And so thus, the image of A, this will consist of the following set of numbers: 1x1, 2x2, 0. So this is going to be, of course, contained in Z3 because that's where it's being mapped to, with the condition that x1 and x2 are arbitrary integers, because this is, after all, an arbitrary vector in Z2. Now, let's write this out. This is equal to, so notice the first coordinate could be anything. So this is anything, because x1 could be anything. But the second coordinate is an even number. It has to be an even integer because there's a multiple of 2. And the third coordinate is always going to be 0. So a convenient way to write out that subgroup is to write it like this. The first coordinate could be anything, so we just write z. Then we do plus. If you want to, you can always also do times, because when you're dealing with a finite collection of groups, whether you use the direct product or the direct sum, it does not matter. But let me just write the direct sum. Then you would write 2z. because the second coordinate always has to be a multiple of 2. And then for the third coordinate, I'm just going to put 0. And of course, by 0, I mean the set, the group, just containing the 0 integer. So the Cartesian product of these three will then tell you that the first one is any integer, the middle coordinate always has to be a multiple of 2, and the third coordinate always has to be 0. So now we can calculate what the co-kernel is. So then, if we do Z3 mod the image of A, we would write that it's Z plus Z plus Z. We have 3 copies of Z. And then we mod out by the subgroup Z plus 2Z plus 0. And now I'm going to use a very well-known fact from a group theory course. And if you've never, I'm sure you've seen it before. If you've never seen it before, it's not difficult to show. But it basically says that if you have a direct sum of abelian groups and you mod out by a direct sum of their subgroups, then the quotient would be isomorphic to the quotient of each individual piece, like component by component. So we're going to have Z mod Z plus Z mod 2Z plus Z mod 0. And this would be isomorphic. This of course is the trivial group, a group modded by itself. This is just the trivial group. This is the group mod 2, and this, well, modding a group by the trivial subgroup, that would just be isomorphic. That's just isomorphic to the group itself. And so in the end, we end up getting that the trivial factor could be ignored, and then you're getting the integers plus integers mod 2. So that is the co-kernel, that if you mod out by the image, this is what you end up getting, right? And basically, I mean, you can kind of see what's going on. Like if you zoom out and you look at what is happening here, you basically just look at the numbers on the diagonal. You have 1 and 2. When you mod out by 1, that gives you the trivial factor. When you mod out by 2, that gives you the integers mod 2. And the reason why you have an additional factor, Z mod 0, I mean, you could say the 0 over here, but I would just say because the image is in Z3, so that's just the missing coordinate. The missing coordinate is just, it's an extra copy of Z. So that's the way you would do it in general. So maybe to give you, let's say, another example, let's say you go from Z5 into Z3, okay, and the matrix here would be the matrix. So it has to be three rows and 5 columns. So let's say it would go like this. Let's say it's -1, then let's say it's 3, and then to make something up, actually, let's say this was -2, 3, and let's just say this would be 1. Okay. So then you'll be able to say that Z3 mod the image of A by the same kind of reasoning. It would be isomorphic by Z mod 2Z, because 2Z and -2Z, it's the same subgroup. Then you look at that one, you would just say it's plus Z mod 3Z and plus Z mod 1Z. So this one will drop out. This is just trivial, so it does not do anything for you. And that would mean that this quotient, the co-kernel, would be isomorphic to that. That's what that would mean. So that's the way you do it when the matrix is in diagonal form. Now, what if the matrix is not in diagonal form? So returning back to this, let's say you have Z to the A, Z to the B, you have A. What if A is not in diagonal form? So this is the like you can say like the big idea of linear algebra, and that is that you can choose bases to represent the linear map in a simple way. In a simple way. And in the simple way basically means in diagonal form. That the way a matrix comes up is when you choose bases. That's basically how matrices come up. That the point of the matrix is to tell you how one set of basis vectors from one space get transferred over to a different basis elements in the other space. Now, some of you might, so here's like a question that you might be concerned about. You might say, is it not true that well, maybe I should say that linear maps in general cannot be diagonalized. And that is true, but it's because you're doing something very specific. So usually, so when you talk about diagonalization in linear algebra, this is usually the setup. You have a linear map, let's call it F. Or maybe I should call it L for linear map. You have a linear map from Rn into Rn. So you have the exact same dimension. And what you want to do is, if you can find a basis x1, x2, xn in Rn. So these are not numbers, those are vectors in Rn, which are eigen vectors for L. That just means that L applied to every xi would be itself, and then you have a multiple, lambda I. Then the matrix that represents L with respect to this basis is, so let's see how it would go. It would be a diagonal matrix for the simple reason that if the rows represent one basis and the columns represent the other basis, so look at what you're doing. You are applying L to this vector, and it's just a multiple of itself. So it's just L1, right? It gets mapped to lambda 1, right? Because it's a eigenvector, it gets mapped to itself. So you're only using one copy of this, but that's the scale factor. And x2, when you apply L, the linear map to x2, it will go to lambda 2, and so on. You get lambda n. So you're getting a diagonal matrix when you do that. But you see, what you're doing is, and this is the important point, is you're choosing the same set of basis vectors for both of them. It's the same one chosen for both of them. You have the same set of basis vectors both for the domain and the codomain. And when you're using the same basis for both, you first insist that it's the same dimension, and you end up getting a square matrix. And then secondly, it's not always possible because you want to keep the same basis for both. Here, we're going to have more freedom. We're going to choose a basis here. What we're going to do is we're going to choose a basis, and here we're going to choose possibly a different basis. So now you have more freedom in how to choose these bases. And here is how this basically works. Okay, so here's, I would say, a lemma, and I'm going to put this lemma on the homework. It's fairly easy to prove. It's going to say that if x1, x2 up to xn in Zn is a basis. So a basis would mean here that every vector in Zn is a unique linear integer combination. So it's integer combinations as opposed to real combinations. A unique combination of those vectors. So that's what we mean by a basis. So if that is a basis, then we can get a new basis by taking one of these vectors, let's say xi, and adding it into xj for j not equal to I. So in other words, this over here, this is your old basis, and now you can create a new basis. going to be your new basis. And your new basis is going to be formed like this. You're going to keep the vectors exactly the same way. And then you're going to have xj prime, and everything remains the same. So you can see everything is the same. The difference is on the xj vector. The xj vector has been replaced. And what is it equal to? So xj prime, it's the original xj plus this new vector that you added into it. So it's not difficult to prove that if you have if you have a bunch of basis vectors, you can modify the basis vectors by adding in one of the basis vectors into a different position. So it's going to be important that it's into a different position. You're going to see why if you carefully work it through. And that's one way you can always change a basis. Now, here is the next lemma. Okay, so here's the other lemma. So the other part of the lemma will go like this. So say you have z to the n into z to the m, and you have a, okay? And you have a bunch of basis vectors. Let's call them x1, x2 up to xn. And then you have y1, y2 up to ym. Okay? And we're going to replace this set of vectors by x1, x2, let's call it xi prime. I'm sorry, xj prime, xn. And these we will keep exactly as they are. Okay? So where xj prime, it's the original xj plus the added in xi. So then the new matrix, let's call it A prime, with respect to this new basis, is obtained by taking the, so I always forget whether it's row or column. It's like one of those things I always have to work through. Maybe there's some kind of mnemonic for this, but every single time I always have to rederive. It's not difficult to prove this, but it's just, it becomes a bit tedious when you have to do it like 50 times. So it's going to be one or the other. I'm not sure, and you'll figure it out. So this is the way it's going to be obtained. You're going to take the jth row of A, and you're going to replace it by, you're going to take the ith row of A, and you're going to add it in to the jth row of A. So basically, A prime is the same matrix, but with its ith row, with its jth row replaced. And you call this row operations. Now, I'm not sure if it's row or column. It could be column. I'm not sure. And the reason why I'm not sure is because you can do the exact same thing with the other one. So you can, if you modify these basis vectors, then you're doing row operations. And if you modify those basis vectors, then you're doing column operations. So it's like you just have to figure out which one is which. But that's essentially the argument. And the result is going to be this. So that if z to the n to a, z to the m is a matrix in general, we can modify A by what you can call the row and column operations. This is just like row reduction, but you have you can also work with columns. So for instance, you can do this. You can add a row into another row. Now you will notice I'm being very careful here. Usually in linear algebra, you talk about adding a multiple of a row into another row. Here you're not allowed to do that. You're not allowed to do that for the simple reason is if you, let's say, if you were to add a multiple of 2, the problem is that's not a reversible operation. You cannot go backwards and use a multiple of a half. You're working with the integers. So that's why you can only add a row to another row. You can subtract them, but that's about it. So you can add a row, or you can add or subtract, right? Add or subtract a column into another column. And you basically turn, and then you convert A into a diagonal matrix. So the diagonal entries in general are not ones. So this is where it's different from typical linear algebra, because when you're working with the real numbers, every non-zero number is invertible. So you can go back, you can, basically what I'm saying, if you have a basis, you can rescale a basis vector. So when you're working with the real numbers, if you have a vector x, you can replace it by 3x. And the reason why that's a vector is because you can also then multiply it by a third and get back to x. But when you're working with the integers, if you take a vector and you rescale it, you cannot, then that means that that vector will only have multiples of 3. You cannot get back to the original x because you're not allowed to use a third. So because of that, when you use these operations, you in general will not have ones, but you will have integers on the matrix. So you get a diagonal matrix, and let's call this A0. And the name of this matrix, this is called the Smith normal form. And like I indicated, I am going to put problems like this on the homework, so you'll get to practice them. They're not difficult whatsoever. So once you see the instructions on the homework, what it asked you to do, that would be the best way to learn this. This is actually fairly elementary. It's just like what you see in linear algebra. And so if you want to find, so if you have the problem of mapping ZA into ZM, then the co-kernel, if you do ZM modded out by the image of A, you can just replace A by A0, because the idea is that this is the exact same linear map, you're just using a different basis. So usually when you're working with Z to the N, you're using like the standard basis, right? So this is what you call the standard basis. 1 with 0, 0, then 1, right? This is what you call the standard basis. The problem with the standard basis is, even though that's the first basis that comes to mind, it may not necessarily be the most convenient basis to use. So it's the same linear map, but you're just replacing it by a different basis vectors here by using the row and column operations, and you end up getting the same exact linear map, but just described by a different matrix. And so you can then reduce the calculation back to this, and we know how to solve this. And then finally, we have this. So let me just clear this away, and let me just say what the final result of all of this is. So most generally, let's say you have Z to the A being mapped to Z to the B, mapped to Z to the C. You have a matrix here A, and you have a matrix here B. How do you find the kernel of B mod the image of A? So here's the way you do it. The kernel of B, you calculate that like you calculate the null space, and then you would get Z to the D modded out by the image of A. Okay, and then the way you get the image of A is by using Smith normal form. You would just say this is Z to the D modded out by the image of, let's say, A0, where A0 is just the Smith normal form of A. And then you know how to solve it. So it's basically the exact same thing, except when you're dealing with the kernel, the kernel of B, it's not necessarily all of this. It would be D, where D is some smaller number than B, but it'll be the same kind of argument. Now, if you're observant, you might make a small little complaint over here. You might say, it's not, is it not the case that this is supposed to be a subspace? So you're right. So I'm being sloppy over here. You can say more precisely what you can say. It's like Z to the D mod 0, where 0 here just indicates a vector of zeros, and it's the appropriate number you need, because technically this is supposed to be a subset of B, so it has to consist of B coordinates. So it's just, if you're not getting all of the coordinates, you just interpret the remaining ones as 0, okay? And that's the way you do the calculation. And as I indicated, the best way to really do this is to work it through as a homework problem, and then you'll see that this is actually fairly simple. So now that we understand how you can compute homology through this linear algebra approach, now I want to show you how this is connected So we're going to use simplicial homology to calculate topological homology. And in order to do that, we need to talk about triangulations first. Now, before we define what a triangulation is, it would be helpful to talk about faces. So recall that delta n, that's the n-dimensional geometric simplex. So this would be the set of vectors. Well, we would just say it's an n+1 tuple. Notice the counting starts at 0, not at 1, in Rn+1, so that every coordinate is non-negative, and the sum, I should have said starting at 1, adds up to exactly 1. So that's what we call the n-dimensional simplex. It's convenient notation to make it live in n+1, but it actually is an n-dimensional simplex because, as you can see, there's what we say n degrees of freedom. X0 is determined from x1 to xn, so there's n degrees of freedom, so it's an n-dimensional object. And we've talked about this thing called the face. We talk about the ith face of delta n, which, let's just write it like this. I'm just going to write x in Rn+1. So for notational simplicity, I'll just call that x. So that the x, actually, let me write it like this. That would be a vector in the n simplex, but whose ith coordinate is equal to 0 itself. So we call this the ith face. So for instance, let's look at delta 2. So this is the way delta 2 would look like. You have the x0 axis, x1 axis, x2 axis, and then you're going to go 1, 0, 0, 0, 1, 0, 0, 0, 1, and those vertices determine a triangle, a solid triangle, which is what we call delta 2. So that would be, so that's what we call delta 2. And now if you take, let's say, face 0 of delta 2, that would just be points in delta 2, so that the 0th coordinate is equal to 0. So if x0 is equal to 0, that means you're right over here. So you would be right there. So that's how it looks like. And as you can see, this is now a one-dimensional simplex. So this is going to be homeomorphic to delta 1. It's a one-dimensional simplex. So in general, the ith face of delta n is homeomorphic to delta n minus 1. And the homeomorphism is actually fairly simple, that if you have a vector in the simplex, you would simply map it to, so you will just, so x is a coordinate of from 0 to n minus 1, and you would just map that coordinate. You would keep everything the same into the ith position. You will insert, let me write it like this. This is xi minus 1. Into the ith position, you insert 0, and then you continue xi all the way up to xn minus 1. So you have added in another number, you just add it in to be 0, and that will give you the ith face because the ith position is equal to 0. So the ith face is going to be homeomorphic to an n minus 1 simplex. And more generally, let S, so this is going to be some subset of coordinates, be a set of coordinates. Then you can talk about this thing called the face with respect to that subset of delta n. And that would consist of points in the geometric n-dimensional simplex, so that xi is 0 for all I in S. So it's exactly the same thing as the ith face, but because you're choosing a subset, you're also possibly specifying other coordinates as well that you want to set equal to 0. We allow the possibility that S is equal to everything, in which case this is what you call the empty face. Okay, so that's what you call the empty face. And if S is the empty set, then the face is just delta n itself. So that we're allowed to be quite general over here. And so it is not difficult to see. So a similar argument will show that the face with respect to that set of coordinates would be homeomorphic to the n simplex minus the cardinality of S. So if you only choose a single coordinate, then the dimension goes down by 1. If you're choosing 3 coordinates, the dimension goes down by 3. That should make sense because every coordinate that you set equal to 0, you're introducing one extra relation, and so the degree of freedom keeps on going down. So to use an example again, let's say we want to find face, and I'm going to write 1 comma 3. That makes no sense. I'm going to write, let's say I write 0 comma 1 of delta n. If you prefer, you can say with respect to the set 0, 1 of delta n, if you like to say that. Maybe to draw a picture better, let's say we do this with delta 2. So the way this would look like is this would be the set of points in the geometric 2 simplex, so that the 0th coordinate is 0 and the 1 coordinate is 0, and the x2 coordinate could be anything. Now the way this would look in the picture is, let's just redraw the picture again, that as before, this is the way we this is how we draw our simplex. So this is the 2-dimensional simplex. And now we're specifying the 0th coordinate is 0. So that means we're not moving on this direction. So we're either on these 2 lines. And then we're saying the x1 coordinate is also equal to 0. And so it's just that point. So it would just be that. So this would just be the set 0, 0, 1. That would be the only way to do that because these have to be 0 and all 3 of them have to add up to 1. So that would just be a single vertex. Okay, and you can see this is consistent with what we're saying over here, that the dimension of this face is the dimension of the simplex minus the cardinality of the set of vertices that you're choosing. So this would be 2 minus 2. So that's how you end up getting that it's of dimension 0. You of course have the silly case that if S is everything, then this would be delta to the n minus n plus 1. And do you get something of dimension -1? Well, of course, the silliness happens because you have the empty set. Sort of the question of how do you define the dimension of the empty set? Do you define it to be 0? Typically, we do not do that. Do you define the dimension to be -1, or do you define the dimension to be -infinity? So there's all of those silly different conventions that people have. We're not going to really worry about it. So that's what we call a face in general. So if we're choosing the ith face of delta n, that's what we call a proper face. That's typically what you think of a face. But something like this is just a face, you can say, in general. That includes smaller dimensional faces as well. This, of course, also includes when S is the empty set. I guess you can call that the improper face. But so that's the definition of a face. So with that, I now want to define for you what a triangulation is. Let X be a topological space. And this is going to be very similar to when we talked about topological graphs. With topological graphs, we had a one-dimensional triangulation, but this is a space in general. So here's the way we define triangulations in general. A triangulation of X is we're going to assume it's a finite collection. It does not have to be finite, but let's not make it complicated. Is a finite collection of continuous maps, f lambda, that map a simplex, a geometric simplex, and we're going to write it like this. This indicates that your finite collection could consist of simplices of differing dimensions. They do not all have to be the same dimension. When we're talking about topological graphs, we're working with one-dimensional simplices, because one-dimensional simplices are homeomorphic to the unit interval. But the reason why it's convenient to allow different dimensions is, just to use a very simple example, let's say you have a sphere. Well, a sphere, the idea is a sphere can be triangulated into many different triangles. That's sort of the idea. You can kind of triangulate it. But imagine that you take a sphere and you add its diameter. Well, then you're getting a topological space that, in order to triangulate the diameter, you have to use simplices of different dimensions. So because of that, it's convenient to make this a little bit more general and not just assume that all of your simplices have the same dimension. So it's a collection of maps from a geometric simplex into your space, so that f lambda is an embedding, so it maps delta n lambda homeomorphically onto a subset of X. Let's call it X lambda. And the following properties are satisfied. So the first property is that if you were to take the union of all of these triangles, so capital lambda, that's just the indexing set. So you think of X lambda as representing your, so X lambda is basically your, quote, triangles. Now, they do not have to look like triangles, but that's the intuition. And these can, of course, be triangles of different dimensions. So they can be a two-dimensional triangle, a tetrahedron, and so on. So your space is the union of all of the triangles. That makes it, it's kind of similar to a graph. Like a graph is the union of the edges. And then the follow-up condition says, now with graphs, we said that two edges intersect in a common vertex or possibly empty. And we're going to say over here that if you take two triangles, X lambda 1 and X lambda 2, and you intersect them, then that would be F lambda I. So when I write lambda I mean both for lambda 1 and lambda 2. This is true for both of them. It would be F lambda I of a face of the simplex. That's what we're saying. It's the generalization of what you have with graphs. If you recall with graphs, the condition was it was the embedding map evaluated at 0 or 1. Because when you're dealing with graphs, you're mapping the unit interval and it's one of the two endpoints. But more generally, when you're working with a simplex, it's going to be a face. When we're saying a face, it does not have to be a proper face. So notice that, let's say, these two triangles do not intersect. So then their intersection would be the empty face. Now, if they do intersect, it's possible that they intersect at like a single point. And then a face would just be a vertex, but that's included in the definition of a face. They could also maybe intersect, maybe something like this, where you have a proper face intersection. So there's different ways they can intersect, and that's what we're saying here. So if you wanted to, you could also write its face S of delta n of lambda I, and then the S, itself depends on I. Well, actually, it depends. It depends both on lambda 1 and lambda 2, but then the notation looks absolutely horrendous. It's the idea that matters, and it's just a face. It's just a face of that one. If we try to write it out in notation, it looks absolutely horrendous, so we'll just leave it like that. So that is what we would call a triangulation. Now, let me give you some examples of triangulations, and I think it is helpful to begin with an example of something that is not a triangulation first, so then you understand the definition a little bit better. So before I write down the definition, give me just one moment to look it up, because I want to just look it up in my note. I do not want to just do it off the top of my head, because I want the labeling to match. So let me just carefully, give me a moment just to look that up. Okay, so this is going to be the projective plane. This is going to be a triangulation of the projective plane. Let's just quickly recall what the projective plane is. So you start with the two-dimensional sphere, and then you have a group of automorphisms that consists of the identity map and A. A is the antipodal map that maps a point to its diameter opposite on the other side of the sphere. And then the projective plane is just defined to be S2 mod that group. So what that would mean is that as a set, so if you write it out as a set, if you have a point, let's say P, on the sphere, you also have negative P on the other side of the diameter. Maybe I should draw a diameter like this, on the other side of the diameter. And then as a set, this will contain P minus P, and so on. It would be pairs of points. So it's not just a point, it's also its opposite pair. And the projective plane is a set of these double sets, And then you put on the quotient topology, and the space you get out of it is what you call the projective plane. So now here's the way we visualize the projective plane. This might not be the best way to visualize it. So the way we often visualize the projective plane is we have the upper cap and we have the lower cap. But there's no reason to include the lower cap because the points in the lower cap correspond to the points in the upper cap. So we sort of just ignore the lower cap. And then what happens is every point in the upper cap is uniquely represented, with the exception if you're on the equator. So if you're located on the equator, then that point has to be attached to the one that's directly opposite across the diameter. Now, it's convenient to just imagine that you make it flat and you look at it from the top-down view. So imagine you're standing up here and you're looking down. Then what you would see is you would see a disk. In the center of the disk, you have the North Pole. Right, so the point on top, you kind of, if you're looking down, you see the North Pole. And then what you notice is that if you're on that point on the equator and that point, they get glued together. And so the way we like to think of the projective plane is we have this disk, and then we just draw this imaginary line through the center. It does not matter how you draw it. You just draw some kind of line through the middle, a diameter line through the middle. And then you're going to say that a point here and the point there, they get identified together. A point here and the point there, they get identified together. They're supposed to be treated as the same thing. This is perhaps the nicest way of thinking of the projective plane because it's the easiest to draw. It's drawn in a flat plane and all of that. And this is the way we're going to think of the projective plane. Now, let's see a non-triangulation first. A non-triangulation. So here's a non-triangulation. So we have our projective plane like this. And let's say you pick, so you have a point here, P, you have another point here, P. And let's say you make up another point. This is going to be Q, and this is going to be Q. And now, if you look at this, if you just look at this like upper portion like this, maybe it would be better to use a different color. Let's say you look at this upper portion like this. You would say that this is a triangle. That's a curvilinear triangle. This side, and that side. And so you can imagine that you're taking the two-dimensional simplex and you're mapping it. Let's call this F1. And then you can do the same thing with the lower triangle. You're mapping delta 2 into F2 because, after all, this is just a triangle. So take the lines, you know, the sides of the three-dimensional triangle, just curve them a little bit, and you get this mapping. And so the question is, so we have a triangulation of P2 consisting of two maps, right? A triangulation is a collection of maps. So you have F1 and F2, right? And the answer is no, because the condition for being a triangulation is that these maps need to be homeomorphisms. And the issue would be is that this triangle, notice that P and P are the same. So what you're saying is that two of these points, there's 2 points of this triangle, they are different in the two-dimensional simplex, but when you're mapping it into the projective plane, they become the same. So it's almost as if you're kind of gluing these together as you map it into the projective plane. So that is not a homeomorphism. So then you can try doing this a little bit differently. So you can say, well, how about we do this? How about we take the projective plane again, cut it up like this and like this. We have P, well, yeah, we have P over here. That's P. We have Q over here and Q over there. Okay, and then in the center, let's call this N for the North Pole. And now you have a triangle, right? That this over here is a triangle. So you have a bunch. So this is a triangle. So you're mapping the two-dimensional simplex. You're mapping this two-dimensional simplex. Let's call this F1 homeomorphically to this portion. You will notice that these three vertices are all distinct. This edge and this edge, there's no overlapping. So this is actually a homeomorphism. So you're mapping this triangle homeomorphically to that piece. That's a homeomorphism. So and then you do it for all four of these. You have one like this, F2, you have F3, you have F4, and then the question becomes, is the collection of these four mappings a triangulation? A triangulation for P2? That's the question that we're asking here. And here, the answer is no. In contrast to the previous triangulation, in the previous triangulation, these mappings were not even homeomorphisms, but now they are homeomorphisms. And the problem occurs. So what's the problem? So the problem is that the triangles in P2 do not intersect in what you call a common face. It's not a common face of intersection. Now, to show you what we mean, let's just look at F1. Let's look at F1 and F2. You're having this mapping, and then you're having this mapping. Now, and then you have another mapping from this triangle. So this is the two-dimensional simplex, that's the two-dimensional simplex. How do they intersect? So you will notice they have this common edge, right? This is a common edge. So that would mean there's like a common edge on this one. There's a common edge, let's say, on this one. And maybe there's a common edge on that one, right? So maybe the way this gets mapped is you sort of rotate it a little bit so this piece gets aligned with this edge right over there. This one gets aligned with that one. You kind of rotate this. This one is sort of being kind of like moved over almost the way that you have it. So that's why they have it in common, but they also intersect at that point P. You see P is there and P is there. So that would mean there's this extra point P here, and then there's an extra point P over there. And why is this a problem? Well, because, well, the problem is that this is a face. This is a face, okay? So this is a this is a face of dimension 1, and that's a face of dimension 0. But the union, the intersection, I'm sorry, yeah, the triangles, let's say, the images of F1 and F2 do not intersect in a common face. Rather, it is a union of two faces. So it's kind of close to almost satisfying the definition of a triangulation, but the intersection set, it will consist of that. It's a union of those two, and that's not part of the definition. It has to be one face for each triangle. So they do not satisfy the required condition. But here is a triangulation. So here is a triangulation for P2. So here's the way you would do it. So it's actually a nice, very nice, pretty picture. You have the circle again inside the circle, inside the disk. You have a triangle, then you have a triangle going like this, a triangle going like that, triangle going like this, and then you add 3 lines like that. And then you give these names. You're going to call this 1. Now, the 1 here does not represent, of course, the number 1. It's just a labeling. Think of that as point 1. This is point 2. This is point 3. This is going to be 1 again because these are on the opposite side of the diameter. This is 2, and that would be 2. This would be 3. This would be 4. That would be 5. That would be 6, like this. And this is now a triangulation. The reason for this is because if you pick, now, let me perhaps write this over here. We usually draw a picture of triangles, but strictly speaking, a triangulation is a collection of mappings. So we get sloppy, so we often leave out the mappings and assume it is understood to the reader that we have mappings. So let's like focus on two triangles. Let's say we take this triangle over here, let's say, and really what this is just a mapping from the two-dimensional triangle, two-dimensional Euclidean triangle, to that piece of the projective plane. And then maybe over here, we have another triangle, two-dimensional triangle, that's being mapped over there. And so we usually do not ever draw this, we kind of just draw the triangles, but it's understood that we have these homeomorphisms. And now if you look at the way these two triangles intersect, they only intersect in that edge, right? This is the edge of intersection. So there's going to be some kind of edge over here, and there's going to be some kind of edge over there. So as you can see, that when you go back to the mappings, when you go back to the domain where you're mapping your geometric simplices, the intersection between these two, it's a face of every simplex. And therefore, you're satisfying the condition to be a triangulation. And then you can check. I mean, it takes some, you have to carefully check for all of them, but once you have that, that would be your triangulation for P2. Now, why are we talking about triangulations? So once you triangulate your space X, you can then use the triangulation to compute homology of X. To compute the homology of X with the aid of simplicial homology. So you're going to turn a topological problem into a combinatorial problem by introducing a simplicial complex. So here's the way you do it. So maybe we make this definition. So say X is triangulated. So it's triangulated in some way. We can call this the corresponding simplicial complex with respect to the triangulation is a set K, so that the n simplices in K, and an n simplex in a combinatorial sense, it's just a set of n+1 points. So the n simplices consist of the images of, let's say, n+1 vertices of each geometric simplex in the triangulation. This is like one of those great instances where when you write it out in words, it might be confusing what we mean by that, but when you see it in an example, it's very elementary what we mean by that. So let's go back to our projective plane example. So we have this projective plane that we drew like this. So that was the triangulation. And then to put in the vertices again, we have 1, 2, 3, 4, 6, 5, 1, 3, 2. So K, this is going to be the corresponding simplex. So here's the way you do it. It has to do with mappings. So you're going to take your triangle, right? So you have a mapping, there's this homeomorphism of that triangle. You have a homeomorphism of that triangle into each one of these regions, right? You have lots of different homeomorphisms. So how do you get, let's say, so how do you get the zero simplices? So the zero simplices would just consist of the images of one vertex at a time. So this vertex, it might be mapped to 2. Then that vertex might be mapped to 1. That vertex might be mapped to 4. It might be mapped to 5. And then you do it with a different vertex. You take a different vertex, and you look at the images. This one might be mapped to 3. This one, under the other map, maybe it's mapped to 6, and so on. So if you actually write out what the images of all of the vertices that you get, so when you use a single vertex, you'll actually get, so that would be the images of the vertices. So these are the the one simplices. So the one simplices, it's just, I'm sorry, these are the zero simplices. So the zero, because these are supposed to be of combinatorial dimension 0. So these are the zero simplices. Then you're going to write down the one simplices. So the one simplices would be the ones that contain 2 at a time. So now you're just going to take every possible combination of 2 at a time. So let's say you take this one and you take that one, and then you find the image of those 2 under, let's say, the first mapping. Let's say this is the first mapping. So maybe these 2 get mapped to 1, 2. Okay, so you get 1, 2. So you get 1, 2. Then you take a different combination. Maybe you take these 2, and then you look at the mapping. So under the same mapping, maybe these 2 now go to 2, 4. So then you have 2, 4, 2, 4. And then you would have 2, 3, and so on. So basically, all you're doing is, I mean, essentially you're saying there's an edge, and you just put it in there. I mean, that's what you do pictorially, but formally speaking, what you're doing is you're just looking at the vertices of these geometric simplices, and you're just finding their images in the triangulation. So there's just the points in the triangulation. And then you're going to look at 3 at a time. And when you get 3 at a time, you would get, like, for instance, 1, 4, and 2, 1, 4, and 2, and so on. So that would be your corresponding. So we call this the corresponding simplicial complex. Okay, that's the corresponding simplicial complex. And where are we going with this? So here's how we're going with this. This is sort of the whole point of this. So this is the theorem. If K is the corresponding simplicial complex of a triangulation of X, then you can compute the homology, the topological homology. It's going to be isomorphic to this combinatorial homology of the corresponding simplex. And that's the idea, that this is hard to compute, and this is easy to compute because you reduce it back down to matrix computations. And that's the idea of how this works. So what's interesting is, I would say, the modern approach to topology is to start with a topological space, triangulate it, and then compute homology. The classical approach is to start with a simplicial complex and then realize it geometrically. So the modern approach is, of course, better because you're ultimately interested in the topology and not in the combinatorics. And with the modern approach, you do not care how you triangulate, because at the end of the day, you're just calculating the homology of the space. The simplicial complex that you're getting, it's just a choice of triangulation. But in the end, you're describing the same space. Now, I would like to show you a nice example of how you would do this. So let's calculate the homology of the projective plane by using this theorem. So this over here is going to be our corresponding complex. And let's compute this. So let us compute the first homology of the projective plane. Let's calculate what that is. So the way we would do this is we would start with one chains. Oh, sorry about that. So what we do is we let K be the previous simplex. The previous complex, a simplicial complex. So it's the one that comes from that picture. I mean, if you want to see it again, you can kind of maybe scroll back the video, take a screenshot of it so it's written out. We're actually not going to do this by hand, so that's why I'm not going to write it out. I'll show you how to do it on a computer program. Doing it by hand is unbelievably tedious. But anyway, so this would be your complex. And to calculate the homology group is you're going to look at the one chains in K, you're going to have the zero chains in K, and you're going to have the two chains in K. And you're going to have the mappings. So the one chains in K, this is going to be the group generated by oriented one simplices. So if you write out the simplices, the one simplices that you have is, to use an example, one of the simplices that we have was 1, 2. Okay, so it's not 12, it's 1, 2, and it's oriented. This is supposed to represent 1, 2, but we're choosing an orientation. The orientation does not matter. You just have to choose something. You just have to orient them somehow, because otherwise you're unable to define what a cycle is. So you just orient them in any way you want. Then you would have, let's say you have 1, 2, you have 1, 3, you have 1, 4, and so on. So it's all of that. You have to count how many you have. And if you count how many you have 15 of them. There's 15. Actually, you have, oh, okay, maybe we should do this one first. This is going to be the group generated by 0 simplices in the complex. So this would just be 1, 2, 3, 4, 5, and 6. So as a group, this is isomorphic to Z6. It's a free abelian group that's generated. Kind of funny, we have a number 6 over here, we have a number 6 over here. This is the symbolic 6 as a label, and that's the number 6. I'm sure we're mature enough to tell them apart. Just like this number 1 over here and that number 1, they mean different things, but I'm sure we can tell that apart. Now, for the 1 simplices, if you carefully look at them, if you look back at the triangulation, you will notice you have between any two vertices, you have a connecting edge. So the number would be Z to the 15, because 6 choose 2 would be 15. And for the 2 simplices, you do not have all of them. If you had all of them, so 6 choose 3 would be 6 times 5 times 4 over 6. So you would have 20. So if you have every single possible combination of 3 as your two simplices, you would have 20 of them. But you actually have half as many. So you just have to go back to that triangulation picture and carefully count them again. This would be Z10. And to show you how this works, yeah, and then you have a linear map. So the linear map, so you have some kind of linear map over here. Let's call this map A, and we have another linear map over here called B. And these linear maps, they're just coming from the boundary operator. So for example, an example of a two-dimensional simplex here would be 1, 2, 4. So what does the boundary map do to 1, 4? So the boundary map of 1 to 4 is, it would be the 0th coordinate. So you have 2, 4. Then you do minus. So the middle coordinate, that's the one that corresponds to the number 1, that's odd. Then you have 1, 4. And then you would have plus 1, 2. So again, these are not numbers, these are just labels. So as you can see, 1, 4, that's one of the, in the basis, you have 1, 2, 2, 4, that's another 1 simplex. And that's how this basis element is being mapped over there. Likewise, that's what the B is doing. If you were to take any one of these simplices, let's say 1, 2, then the boundary of that would be 2 minus 1. So again, this is not 1, that's just a label. That's just a formal sum of 2 labels. So that would just be 2 over here and 1 over there. So you have to find what these matrices are when you're using these bases to represent them. And let me show you how you would do this in a computer program, so you do not have to waste an enormous amount of time doing this yourself by hand. So I'm going to switch screens here, and there's many different pieces of software that you can use. I'm basically using R software. So R, as you probably know, is a popular program for statistics, for statistical analysis. It's free. That's probably the most popular software. So very frequently when you teach courses, this is the software that is used. And I'm using, the service that I'm using is completely free, and you do not have to download anything. So if you do not have any software for doing mathematics, I would recommend to use it. So you just go to POSIT Cloud. In the old days, this used to be called R Cloud, but I guess a different company perhaps bought them. So now it's called POSIT Cloud. And once you log in with an account that's free, you will click on New Project. You will create a project, you give your project a name, and then you log in. So then you wait till it logs you in, and I'm going to show you how to use it. It's actually very easy to use this. So here, what you will do is, yeah, so this is what you will do. You will just click on File, and after you click on File, you would select New File, R Script, and it will create a window for you where you get to type in some code. Now, I already did it over here, So I'm just going to, I mean, this is basically notes, so ignore that. So first I'm going to create my matrix. So maybe I should make this a little bit bigger. Let me make this a little bit bigger so it's easier to see. Maybe make it bigger just a little bit more. Okay, so I'm going to create my matrix. And if you recall, we're going to have, so you use hash for commentary. So we're going to have a map from Z15 into Z10. Okay, so this is going to be two-dimensional chains, and these are one-dimensional chains. So the matrix will have 10 rows and 15 columns. So I'm going to begin by creating a matrix, and I'm going to write A is matrix. I'm going to just make it a matrix filled with zeros. I specify the number of rows. I specify the number of columns. And now here's the way you execute this. If you select the line and you click on this button called Run, in the environment panel, you've created, you see you have the environment panel, you've created your matrix. So now if you click on the matrix, it will open up a window for you. So this is your matrix where you can just explore your matrix. You can see 15 rows, and it's just filled with zeros everywhere. So the next thing that I will do is, it would be convenient, so if you look at your matrix, this is not very convenient. This is column 1, column 2, column 3. It's not clear what the numbers correspond to. So we're going to rename the columns. So the columns will be the two-dimensional simplices and the oriented two-dimensional simplices, and the rows would be the oriented one-dimensional simplices. So in order to do that, I already did it over here in advance. So this is the way. So let me just show you how you do it. So the first thing that you do is you would type row names A. So this means you're going to replace. So at the moment, the rows are just called by numbers: row 1, row 2, row 3. That's not convenient. So I'm going to replace the row names. So by all of this. So C, that stands for combine. That stands for combine, and this is the vector. It's basically a vector. So I'm going to copy this. So this is basically how you write it out. Right, so it's combine, so it's like vector. This is the first coordinate, this is the second coordinate, that's the third coordinate, that's the fourth coordinate, and so on. And by putting them in quotation marks, I'm telling the computer to treat that not as numbers, but as symbolics. So those are just symbolics, and those represent all of the oriented one-dimensional simplices that we have in our complex. Now, you do not have to go to the next line. I just did it to make it look nicer. You can all write it in the same line. You can, normally what you do is to make it look maybe nicer, you can do this, perhaps, like this. So this is just a way to, kind of organize it in a nicer looking way, like this. Okay, so as you can see, it shows you where the bracket begins and closes off. So by doing that, if you now execute this command and you click back on your matrix, you've made your matrix look a little bit nicer, because now you can see that your rows are named after the oriented two simplices that you have. So that's the way that you do this. So you've given your row names. And then you'll do something very similar with the column names. So I did this ahead of time myself, so I'll just copy this again. So I did this ahead of time, and just like before, we'll just organize it in a nice way, like that. And we give it, that will be the column names. So these are the oriented two-dimensional simplices. We run this, and now if you click back on your matrix and you explore your matrix, you can see the columns are now more conveniently named after every two-dimensional simplex. Okay, so the next thing that you need to do is you're going to apply the boundary operator. So you're going to take every single one of these, and you're going to apply the boundary operator, what we were saying. So like, for example, 1, 2, 4. So how do you express the image of 1, 2, 4 under the boundary operator? So the first two, 1, 2, there it is, 1, 2. That means 1, 2 will have the number 1. But if you remove the middle 1, 2, you're removing the odd index. That's the one that corresponds to the coordinate number 1, because it's 0, 1, 2. So by removing 2, you're left with 1, 4. So 1, 4 will have to be -1, and then the other one, 2, 4, which is all the way down here, would have to be 1. The other ones will remain as 0. Now, the way you insert something like that is actually very simple. So I'll do the first line for you. I'll do it right over here. So you just manually, I do this manually, and it really only takes around 2 minutes to do. It's not that tedious. So what this means is, so in matrix notation, That's the row, and that's the column. Now, because we have labeled our columns by these symbolics, all it means is I'm telling the computer to look at column that's labeled by 1, 2, 4. Okay, that's the column. And what rows do I want to select? So I want to select 3 rows at the same time. So this is the way you input this. You put the combined vector. You want to select these 3. So you say select those 3 rows corresponding to those symbolics. Look at that column, and then replace those 3 rows at that column by the numbers 1, -1, 1. So that's where it comes from. So as you can see, as we said before, 1, 2, the one that corresponds to 1, 2 gets replaced by 1. 2, 4, 2, 4, that will be replaced by 1. Whereas 1, 4, the first one and the last one, 1, 4, that gets replaced by -1. So by doing that, so if I just run that and I look at the matrix, this is exactly what we were saying. You have 1, you have -1, and the other one will be down here. And now you just do this for the remaining ones, right? You just do this for all the remaining ones, going like this. And then we'll just put it in here. This is somewhat tedious, but you can do this yourself. And when you run, you would have done this for all of the rows that you want, all of the rows and the columns that you want to. So it's done. And now you're going to do the same thing. So this was the map from Z15 to Z10. You have another map that goes from one-dimensional chains to two-dimensional chains. I'm sorry, to zero-dimensional chains. So it's from Z10 to Z6. And for that one, you do the exact same thing. You're going to create a matrix. Okay, your matrix, in this case, would be, so this time it would be, oh, sorry, there is a mistake here. I wrote Z15. I think, let me look back. I think number of columns is 15. So the number, yeah, I just got it back. Yeah, it's not. I meant to say from Z10 to C15. Sorry about that. It is written correctly. I just misspoke up here. And this one will go from Z15 to Z6. Yes. So that's the way we had it set up on the board. So that would be the way you input your matrix exactly as before. And then you're going to do the exact same thing. You're going to give the column and the row names. So I'll copy that. I'll just briefly go through this again. So the column names, so this is the same thing, but now instead of the row names, it's going to be the column names for B. And the row names for B would be the zero simplices. So these are numbers from 1 to 6. So if we run this one and we look at the matrix B, as you can see, these are 1 simplices. There's 15 of them. And then there's 6 zero simplices, as you can see over here. And now what you do next is very similar to what we did before. You will define all of those new rows and columns. So you'll copy, I'm just going to copy. So again, you manually do it. It's not very difficult, pretty straightforward. It takes like 2 minutes to do this. So all you're saying is you're going to look at the column of B, right? So matrix B, at that column, you're going to find 2 rows, the one that's labeled 1 and then one that's labeled 2. And you can see 2 is the endpoint, 1 is the beginning point. So 2 gets replaced by 1 and 1 gets replaced by -1. So you notice the 1 and the -1, those are not symbolics anymore. That's a different color. Those are numerics. The ones in green, those are the symbolics. So you do that, you run, right? You run, and then just like before, you end up creating this matrix. So you see 1, 2, that's 2, 1, 1, 3. This number is 3. This number is -1, and you just do that for all of them. And now you have to install a package. The purpose of this package is to do what we call Smith normal form. So there are online calculators, but I think this is the most convenient way to do it. So you're going to install a package. This does not come with the base version of R, because there's hundreds of thousands of packages. You do not want to install everything there is. That's too much memory. So you just pick what you want. So you click on where it says packages down here. You have like a panel down here. Click on packages. You say install, and you're just going to write over here the name of the package, and it's called QU Homology. That's the name of the package. It locates it for you, so it's a recognized package. You click install, and after it installs the package, you just have to find the package. You have to load it. So you just have to find it. So there it is. So what it's, I actually have no idea what this is. So they said this is the calculation of homology of quandles, racks, biquandles, and biracks. I've never seen what biracks or racks are in homology, but someone apparently written a package in R for doing that kind of calculation. So you just have to load the package. So you can also type in that, but now that the package is loaded, you can do Smith normal form. So okay, so how do we therefore solve the problem? Well, basically, to use this as our board, we're going from Z10 by using matrix A into Z15, and we're going from Z15 by using matrix B into Z6. So these are the linear maps that we have over here. Now, to find what the kernel is, that's basically row reducing the matrix. So you can do this by using Smith normal form. So you would type, so what do you want? You will type, it's called Smith B. You want to find the Smith normal form of B. So you would execute this, right? You execute, and when you execute, it shows you the answer down here. So let me just make it larger. So as you can see, those are just the column names, those are just the row names, and this is Smith normal form. It's just ones down the diagonal, and then you have a 0 over here. So what this is saying is, I'm going to switch over to the other board to make this easier to understand. So let me, for the moment, switch back to our main screen, and we'll work this out. So this is our main screen. So on our main screen, we have a mapping from Z15 to Z6, and we call that B. And what we're saying is, by choosing, you can always choose bases, so this is convenient. And what we saw is, by choosing appropriate bases, this is just 1, 1, 1, 1, 0. Smith normal form, and everything else is 0. So now you can find the kernel of B, right? So now you can find the kernel of that B. And the way you find the kernel of B is you would say that this would contain a vector of 15 components in Z15. So that, and then this is telling you, so you're saying that 1x1 is 0, 1x2 is 0, 1x3 is 0, and 1x4 is 0. And then the remaining ones, x5, x6, x7, and so on, up to x15, those are the remaining ones. Those are anything. Those are anything that you want. So really the kernel would be 0 times 0 times 0 times 0, and then you would have copies. You would have 14 copies. Not 14 copies. You would have 11 copies. You would have 11. I'm sorry, that makes no sense. You would just have 11 copies of Z, right? The first 4 coordinates, right? This is what you get, and the other ones are just, there's no conditions on the other ones. So the remaining ones, they could be anything that you want. So that would be the kernel. So that right there would be the kernel of B. So the kernel of B in this case, as you can see, it's isomorphic to the group Z to the 14. Z to the 11. You see, that's what we're saying. In general, the kernel would be Z to a smaller dimension number, and that's what it is. So that's what the kernel is isomorphic to. Now, what do we do with the other one? So with the other one, that's the one that goes from Z10, this is matrix A, to Z15. So to calculate what that is, we're going to use the Smith normal form. So let's go back to the computer and ask it to calculate for us. So you can open this up again, and in this script window, you're going to type Smith A. So you would type that in, and then you will execute the command, and it will show you an answer that comes up. Okay, so these are all of the rows. These are all the columns, and you notice you have ones everywhere. But then there's actually a small mistake here. There's a small mistake. It seems that the code, this is kind of common when you're doing code, that when you're writing a loop, you're like off by 1, and it seems like they're off by 1. This is supposed to be a 0. And you can see that it's a 0 because if you subtract this second to last column from the last column, that number will just become a 0. So it's just, I mean, what would it be? So let's count how many. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 ones. And then you have 2. That's 9 ones. Then you have 2. And then the remaining ones are going to be 0. So that's what you end up with. So let's go back to our board and say what we get for the Smith normal form. So for the Smith normal form over here, we get that this is, so this is just going to be 1, 1, 1. Then we would have, sorry, this is 1, 1, 1. We get to 2, and then we have 0 here, and we have zeros, and we have zeros like that. Right, so there's zeros there as well. So this is what we end up as our answer. That's the Smith normal form for that. And now we can compute the homology by using this. So to compute the homology, we would have to take the kernel of B and mod out by the image of A. The image of A. So now, to make this perhaps a little bit easier, so maybe we should do this. Let's do this like we did before. Z15 mod the image of A. I think this will make it easier to do it like this first. So Z15 mod the image of A, you would just, so that would just be Z mod 1Z plus Z mod 1Z plus Z mod 1Z, and then plus, but you have all of that plus, right, plus, then you have 2, right, so you have 9 of these, 9 factors, then you have Z mod 2Z, okay, and then you do plus, you're going to have Z plus Z, have 5 copies. Oh, sorry about that. The other ones are 0, right? The other ones are, yeah. So you're modding out by 0, right? You're going to be modding out by 0. So you'll have 4, right? You have 4. So this would be 1, right? There's 1, and then you have to have 4. No, actually, you need to have 5, right? You need to have 5 of those. So you need to have 5 of those. And now I noticed a small mistake, but it's not serious. And the mistake is that if you carefully look at the computer, there's supposed to be an extra 1 over here. So I forgot to include that extra 1. And so the kernel would actually, it would have, there's 5 zeros. There's 5 zeros, right? So there's 10 of these. So the kernel would therefore be a 10-dimensional space. And so when you're computing, so the kernel is a 10-dimensional space, okay? So this is the way you would compute the quotient if you go all the way up to Z15. But the kernel is a 10-dimensional space. So what the modification is, you just replace it by Z to the 10. So that's the modification. Because again, if A is being mapped to Z15, then that would be Z15 mod the image. but the kernel is z to the 10, right? When we're computing homology, how do we compute homology? We're computing homology by taking, so we have z to the 10 to z, this is a, by z to the 15 to z to the 6. So to find homology, this is map B, we take the kernel of B mod the image of A. It's not z to the 15 mod the image of A, it's the kernel of B, but the kernel is z to the 10. So you essentially treat, it's the same calculation, but it's from z to the 10 to z to the 10 by the same, it's the same idea, but you're modifying this dimension. And so what would happen is, instead of having 9 factors, so if you were to replace this by z to the 10, which is the kernel, by the image of A, then what would happen is you would have, as before, you would have 9 factors, 9 trivial factors, then you would have z mod 2z, and then you have no remaining factors because this is exactly z to the 10. So you have no extra remaining factors. So these are not supposed to be present because you have exhausted all of your factors. And so in the end, these are the trivial factors, so they all go away as well. And there's only one factor you're left with. And so we have shown that the first dimensional homology of the projective plane is isomorphic to z mod 2z. Interestingly, that is also isomorphic to the fundamental group. So you might wonder, is the fundamental group and the homology group the same thing? Now we know they cannot be the same thing because fundamental group does not have to be abelian, whereas the homology group has to be abelian. So a reasonable question to ask is, if the homology group is abelian, then does that mean that's isomorphic to the fundamental group? It should not be a surprise because homology is defined in a very similar way. It's sort of inspired by homotopy, but it's done a little bit differently. So the fact that you're getting the same answer, it should not be too much of a surprise. But we'll make it more specific when the time becomes appropriate. And then if you're interested, you can use the exact same procedure to find, so how would you find, let's say, the 2-dimensional homology of P2? Like how would you get that one? Well, here what you would do is you would consider 2-dimensional simplices in the complex, so that's the corresponding complex. You would map it to C1, and then you would have 0 because there are no 3-dimensional simplices. And this is z to the 10, and this is z to the 15. And now we're not interested, and this is our matrix A from before, but now we're not interested in the image, we're interested in the kernel of A. And to find the kernel of A, just like what we did before, you write out the Smith normal form. And this is what we ended up getting, right? We kind of written it all the way here, right? That would be the Smith normal form. And so to find the kernel of A, so the kernel of A, that would consist of vectors in z to the 15, so that A of the vector, so if you write out these conditions over here, so that 1x1 is 0, 1x2 is 0, and then you have 2x 2x2 2x10, I guess, is 0. I think I'm doing something wrong again. So we have this from Z10 to Z15. Did I mess this up? Yeah, I messed it up. It's from, yeah, I messed it up. So it's from Z10 to Z15, right? From Z10, this is in Z10 to Z15. So, yeah, and so like and now if you look at this, yeah, that should be Z10. If you look at this, this is telling you the first coordinate has to be 0, the second coordinate has to be 0, and the last coordinate has to be 0. So in other words, the kernel, it's just the trivial group, okay? And so the two-dimensional homology of the projective plane is trivial, right? That's what that means. So this is the way these calculations work. It's fairly algorithmic, and with a little bit of practice, it's not too difficult to do. So now let's discuss the question of improving computation. And it's basically, do we really need this many triangles for a triangulation? So let's say for P2. So for P2, we use 10 triangles. Do we really need that many? And it turns out that we can improve, we can generalize triangulations of a space to simplify computations. And so I'm going to borrow this from Alan Hatcher. So this is a generalization. This is a weaker, this is going to be weaker conditions. And they give you a bit more freedom to triangulate your space so that you do not have to use as many triangles. So here's how this goes. I'm going to make a definition. This is the definition. Let X be a space, a delta decomposition is a collection of maps F lambda from a geometric simplex into your space, so that now with a triangulation, we want these to be homeomorphisms. But sometimes that's a little bit too restrictive. We can loosen that a little bit. So that F lambda maps the interior of your simplex. So I'll define what the interior is in a moment, but you just stay away from the boundary of your geometric simplex. It maps the interior of your simplex onto a subset of X. Let's call it X lambda with a little interior symbol on top of it. So F lambda maps the simplex onto X lambda, not necessarily a homeomorphism, but if you take this subset, so if you take that subset of that geometric simplex, it will be mapped to a subset of that one, and this mapping is a homeomorphism. Just a small comment about the notation. This is not exactly the best notation, because this notation seems to suggest that it's the interior of the image. Okay, so this is not the interior of the image of that. It's just the image of the interior. Whether the two are equal, we really do not care. That's just not part of the definition. So it's not exactly the best notation, but let's keep it like this. And what conditions are satisfied? So that X is the union of all of these. So this is a finite collection. If you look at Hatcher's book, he actually considers the possibility where you have an infinite collection of these, but let's not even bother to go there. There's that coherence condition that has to be placed. It's very similar to when we talked about topological graphs, but I really do not want to go there. So that X is the union of those. And the collection of these, the images of the interiors, these are pairwise disjoint. So there's no overlapping. There's no like double counting or anything like that. And then finally, and this is like the technical condition, but you'll see why we want this. So at the moment, so this is not clear why yet, but you'll see why we want that. And finally, the other condition is that if you take one of these maps, f lambda, and you restrict it to one of the faces, so if you restrict it to one of the faces, then this would be equal to some other mapping in your list. So that would be, let's say, f mu for some mu in the indexing set. So by restricting, so basically what we're saying is you have these maps from this simplex, they're defined on that simplex. If you were to restrict these maps to any one of the faces of the simplex, that would then give you another map in the list of maps that you have in this weaker type of triangulation. Now here we are being abusive in the notation. We're just using this fact again that the ith face of the simplex is homeomorphic to its dimension minus 1. So when we're saying that this is equal to some other simplex, it would mean that the corresponding dimension is 1 less, and that really this is being composed with that homeomorphism, but that would just look way too messy of a notation. So we just assume that the reader can fill that in. The one thing I did not actually mention is how the interior is defined. That's actually defined in a very simple way, that the interior of the n simplex, these would be points in Rn. Well, let's say it's points in delta n, so that every coordinate is positive, strictly positive. So that ensures that you're staying away from any one of the boundaries, because the faces are obtained when you set them equal to 0. That's what you call the interior of your simplex. Okay, so now the next thing that I want us to say is, what do we do with this? Let me give you an example. So delta decompositions are more general than triangulations. So they give you more freedom. I guess maybe this is like a good question to think about why that is. It's not really difficult. You just have to run through the definitions why it is. I mean, because basically in a triangulation, this is a homeomorphism. So then if you restrict the homeomorphism to that interior, then that would certainly map that homeomorphically to the image. This will also be a homeomorphism. Right, so if you restrict that, I'm going to call it f lambda again. That would again be a homeomorphism because that's just a corresponding image of that. And also the interiors do not overlap for the simple reason, because if two triangles overlap, they only overlap on their faces. Right, that's the assumption. They only overlap on their faces. So if you stay away from the faces, then the interiors are non-overlapping. So delta decompositions are therefore more general. Okay, so let me show you a delta decomposition for the projective plane. So here's how you can do it. So you take your projective plane. So let's call this P. So that has to be P again. Let's call this one Q. Let's call this one Q. Let's call that N for the North Pole. Actually, we're not even going to do that, right? We're just going to, then I'm going to call this E. So this is going to be an edge. We're going to have another edge. Let's call it F. F. So it's just a, and then you're going to have something that goes like this. Let's call it G. Okay. So, and then you're going to have this triangle, so that you can see this 3 vertices, so it's sort of like a triangle. Let's call this U for upper, and let's call this one L for lower. So this is, of course, just a picture, but more formally, more carefully, you write down a picture of a triangulation, but of course, it's supposed to correspond mappings. So here are the mappings that you have. P is supposed to be a mapping. So P is a mapping from the 0 simplex into the projective plane. The 0 simplex is just a point, right? But we're using mapping, so you're just mapping that. So we're calling it P in the picture, but this is a mapping, right? You're just assigning a single point to that one. Q is a mapping into P2. So you have 2 vertices. And then you have E. E is this map. So E is the mapping from the 1 simplex, into P2. Okay, so this is the 1 simplex. The 1 simplex is homeomorphic to the interval, so you're just taking that interval, right? So all what we're saying is just take your 1 simplex, that's delta 1, and map it in a way so that point goes to P, that point goes to Q, and it's just being mapped like that over. Then you have F. It's from the 1 simplex into P2. And then you have G. That's from the 1 simplex into P2. Now look at this. This one is a homeomorphism. Well, I want to just clarify something. When I write homeomorphism, I'm being sloppy. I'm not saying it's a homeomorphism, obviously, with P2. I'm saying it maps the 0 simplex homeomorphically to that point. Right? You're just mapping 1 point to 1 point. This one is also a homeomorphism. And E is a homeomorphism onto a subset. And F is a homeomorphism onto a subset. So maybe what I should write is maybe I should put P. So P2 subscript P. So it's the subset of P that corresponds to the image. So maybe that would be the better way to write it. Now, this one, the G, is actually a little bit more interesting because G, these are the same in the projective plane. So if you take the 1 simplex, right, the 1 simplex, which is this, that's the 1 simplex, delta 1, you're mapping that point to P, you're mapping that point to P. So the mapping to this diameter, so basically this is, so this is the one that, so this is actually like a circle in the projective plane because these two come together. This is no longer a homeomorphism. So these are homeomorphisms, but this one is not. But, and this is the whole point, but if you look at G from the interior of the 1 simplex, it will then be mapped homeomorphically to the interior, to its image. I was almost about to say the interior of its image, but that's not maybe necessarily true. We do not really care if that's true, but you see, because if you go back to this 1 simplex, these points are going to P. But if you stay away from the points and you just look at this interval, it is being mapped homeomorphically to that interval. And so then you're safe. And then you also have, and then the other maps that you have is you have 2 other maps here. And the 2 other maps that you have are U and L. So U, let's remove this one, let's remove this one. Then you have U, and this is a map from the 2 simplex into P2, and L will be a map from the 2 simplex also into P2. And now observe that, so this is the triangle, we're mapping this triangle to this triangle, right? You sort of just imagine you take this edge, you round it out, you take that edge, you round it out, and then you take that, so you're mapping it. So when you're doing these mappings, you do not really care what the formula for the mappings are. That does not really matter here. You just care that you have such mappings. So you never actually write out the equations because they would be too messy. You do not really care about that. But you have these mappings. And so now that you have these mappings, you should notice that this is not a homeomorphism because you can see these 2 points, they come together. So that's not a homeomorphism, but in a way that's okay. That's the point of a delta decomposition. And now let's check. So if you restrict U and L to the interior of the simplex, then you get the sort of interior, like you're staying away from those edges on the boundary, and then that is a homeomorphism. So let's check. So we have a delta decomposition of P2 with a total of 7 mappings. So we have, so these over here, so these two, we will call them in quotation marks the triangle. So we have 2 triangles. We have, in quotation mark, we have 3 edges, and we have 2 vertices. So we have achieved a delta decomposition of the projective plane by using a much smaller number of vertices, edges, and triangles. But let's actually confirm that it satisfies the conditions of a delta decomposition. So, well, it's clear. So the first condition is it a homeomorphism? Are these homeomorphisms on the interior? So are these mappings homeomorphisms on the interior? Yes, so that's what we observe. Then are the interiors non-overlapping? Yeah, so just look at the picture. The interior of these two, well, that's just the empty set. I mean, there is no interior. That's just the empty set. There's nothing to do here. Now, the interior of E, if you look at its image, you're staying away from those endpoints, and you're staying away from those. And then on the G, you're staying away. So those are non-overlapping. And then the interiors for U and L, that's just the inside for U and the inside for L, not touching any of the edges. So you can see from the picture that the interiors are non-overlapping. And then the technical, and this is the technical condition. And again, as I said, it's not clear why we want this, but this is the technical condition. So this is like perhaps the most complicated one. So is it true that the face of each mapping is included in this list? In this list of 7 of them. So basically what we're asking is this delta decomposition, well, technically what we want to check is the delta decomposition, you can say closed under the operation of faces. Is it closed under faces? I mean, a very strange way to put it, but maybe you find that helpful. Just like we talk about a subgroup being closed under addition or multiplication. Here, the operation that we're doing is we can calculate the face of any simplex and then check of whether or not it's back in this list. So let's look at these two. Let's look at E. E, like we have not written out the formula for E, but what is E doing? E is taking the one simplex and it's mapping it to this piece. So that vertex goes to P, and this vertex goes to Q. So if you look at the face of E, E has 2 faces. It has 2 faces. So the mapping of that point to P and the mapping of that point to Q. But that's already included in our list. So there it is. That's already included in the list. So the faces of the edges are included among the vertices, under the vertex mappings. So now let's look at the other ones. Let's look at U and L. So what is U doing? So U is taking a triangle and it's mapping it so that this side goes to that one, this side goes to that one, and then that side goes to G. So you can therefore ask, how do you know that when you restrict the U map to this edge, it's going to give you, so this map from Q to P, how do you know that that's the same thing as F? Well, technically you do not know that, because you actually have to look at the formulas for U and L and confirm that the formulas for U and L are consistent with those 3. But here's a very simple way out of it. You can just start with U and L, right? U and L with these 2 homeomorphisms, and then they have 3 faces. And the faces that you get, this face, that's a 1 simplex, right? That's a 1 simplex. And whatever face you're getting out of that, you just define. So this is the one that's going from Q to P. So this is the F. So you would just define F to just be U restricted to that face, right? So you just basically do it by construction. You start with U and L, and then you force E, F, and G to be what you get when you restrict this mapping to each of the faces, and then you're automatically guaranteed to be safe. So this is what we have. So yes, this decomposition, this delta decomposition is closed under faces. So what's the point of all of this? So so this is coming from Alan Hatcher. So here is the main idea of why we're doing this. So behold, P and Q are are zero chains in P2. So recall the definition of a zero chain. A zero chain, by definition, is a mapping from the zero simplex into your space. E, F, and G are one chains in P2. And U and L are two chains in P2. Now here's the big idea. So this is the part which makes this very nice. I would say this is sort of like the big idea of what we're doing. When we work with topological homology, so not simplicial homology, topological homology, it's also called it also goes by the name of singular homology, for the simple reason because the word singular in mathematics means badly behaved. So it goes under the name singular homology because these mappings, we do not assume anything about those mappings. We do not assume that they are homeomorphisms or anything like that. That's why we call it singular homology. But I like to call it topological homology. So anyway, so when we work with topological homology, chains, so let's say n chains, this is the free abelian group generated by all maps from delta n into your space, into some space x. And so Cn of x, this is a enormous group. It has an uncountable number of generators and all of that. So what Alan Hatcher says is, if we have a delta decomposition for x, we can smallen, to make up a word, make smaller, or let's say shrink. We can shrink these chain groups, these chains, by replacing them with, so let's call it Cn of x and put a little delta over here, indicating this is the chains that are coming from the delta decomposition. So this is going to be the n chains. This is the free abelian group generated by the n chains in the delta decomposition. So instead of all mappings, you're only going to look at the ones that are coming. So in other words, i.e., is going to be the f lambdas from delta n into x. That's what it's going to be. You're going to look at those lambdas, f lambdas, that are defined on the n simplex, and you're only going to use those. That's a finite number, right? This is a finite number of generators. Now, then we have, oh, okay. So the assumption that these maps, f lambdas, are closed under faces implies that the boundary map takes n chains in your delta decomposition and it will assign n-1 chains in the decomposition. Because how is the boundary map defined? You you take a chain, and then you look at each of its faces. And when you restrict the mapping to the faces, you're getting mappings from the n-1 simplex. But by assumption, when you restrict these mappings to the faces, you stay within your delta decomposition. So because of that, this gets mapped to this. And here's sort of the theorem. And this is very technical to prove. We're not going to prove this. I do not think it's appropriate to try to learn the proof of this theorem when you're learning homology for your very first time. Alan Hatcher proves that over many pages. I have no idea, like 10, 15, 20 pages. There's a lot of lemmas. There's a lot of other things that you have to talk about. He talks about the homology relative to a covering. Then he talks about homology relative. Then he talks about something called relative homology, and he kind of puts the whole things together, and then you end up getting the proof of this result. But let's just say what the theorem. So it basically says this, that if you want to calculate the homology of your space, that's the same thing as calculating the homology of your space using that delta decomposition, where this homology is being calculated by this shrunk group. This is the group where you only look at the n simplices coming from your delta decomposition. So if you're willing to accept this result, let's do an example. So we'll do the example with the projective plane again. So going back to our projective plane, we call this P, this is Q, we have F, we call this one E, we call this F, we call that G, this is upper, this is lower. So we have the zero chains. So you would say that's the group that's generated by, it's the free abelian group, so the generators for this group will be P and Q, right? So that's the group that's generated by all formal integer combinations of these two zero simplices. And then you have C1, right? So of course this is as a group that's isomorphic to Z2. Then you have C1 of X. So this is the group that's generated by the one simplices. So here you have 3 one simplices in total. So you have E plus F plus G. So as a group that's isomorphic to Z3, you can immediately see the dimensions on these immediately become a lot smaller. And then you have C2 of X, and that would be UZ plus LZ. So as a group, this is isomorphic to Z2. And we're going to compute, as before, we're going to compute the first homology of X. So X over here represents our projective plane. And we'll do that by saying that this is isomorphic to the homology coming from the delta decomposition of the projective plane. So how do you find this shrunk homology? Well, you're going to go from, so actually, small little mistake, I should have put that little triangle on top because we're not considering all mappings, but only the ones coming from our delta decomposition. So you're going to go from C1 of X to C0 of X, and here you will go from C2 of X into C1 of X. So this one is going to be, of course, Z3. This is going to be Z2, and this one is going to be Z2. So you'll have some matrix here, and you'll have some matrix here. And we're going to actually find the Smith normal form by hand to do that calculation. But first, so let's figure out what B is. So we need a basis for this one. So the basis is P and Q. So the matrix B, this is going to be 2 by 1. So the basis for this one, for C0, consists of P and Q. And the basis for that one consists of E, F, and G. So E, F, and G. So now you're going to apply the boundary operator for E. So it's always a question of orientation, how you map it. So let's say, you see, the one simplex by definition is, well, the one simplex, it looks like this. It's a subset of R2. And as we said, the way we orient the one simplex is we first set, this is x0, well, we set x0 to be 1, and this is x1 to be 1. So we orient the simplex from the smallest value, well, from the initial, from the x0 coordinate to the x1, so it goes like this. So if you just imagine picking that up and mapping it like this, let's say. Well, actually, maybe I should not do that because, yeah, maybe what I should do first is I want to be a little bit careful here, because remember how we're getting U and L. The way we're getting U and L, I'm sorry, the way we're getting E, F, and G is we first begin with U and L, and then we restrict it to the faces to get E, F, and G. So here's the way we're getting U. So it's a 2 simplex. So this is the 2 simplex. That's the 2 simplex. So therefore, just imagine that this side, this is the one that's going to G, right? That's the one that's going to G. So this one goes here, that side goes there, that side goes here, right? You just pick it up in the most natural way without doing anything to it, and you just kind of like pick it up, and you could just put it here. So this is our mapping U, okay? So let's therefore calculate the boundary, well, so this over here, that's the one, this is the one that goes from P to Q, right? This is the one, so that's actually going to be from P, right, this one. So this one, so that's the mapping that we have over here, right? The one that goes like this. So I guess that would mean that F, so you're going from, so you want F, let's say. So this is going to be F. So, so this edge, the orientation, you're going from x0 to x1. So it's like this, right? Like this. And this edge over here, right? That edge. So if you're traveling like that, you're going to, this side is being mapped from P to Q like this, right? So in fact, as you can see, so then the correct way, if you want the F to be consistent with the U, it has to go like this, right? So that's the way the F. So you start, yeah. So you're starting, as you can see, you're starting at P and you're going to Q. Starting at P and you're going to Q. Like you can also say this is F, right? That's going to be F. So that's F for you, right? So I think maybe it's easier to kind of look it up here. So F is the map where that point goes to P and that point goes to Q. So, and what about the other one? What about E? Well, E, so I think I made a mistake. I'm going from P to Q. From P to Q. Oh, so I actually have, yeah, I have different, so this one from P to Q, yeah, so the F goes like this then. It maps, it takes the initial point, sends it to P, and the terminal point goes to Q. So that's how F is being defined. So its terminal point, its initial point, its terminal point is Q and its initial point is P. So that would mean the boundary would be, so 1 minus the initial one. The G, that's the easy one, right? The G, that's the one that's easy because you can see G begins and ends at the same point. And if you work it for the other one, this one's going to go the other way. So this one's going to be 1 and -1. Now, if you want to see why that is, yeah, so if you want to see why that is, let's just work it out over here. So E, you're going from Q to P. So this E over here, it's the same E as on the other side, right? This E and that E, that's the same E. And the orientation is you're going from X, you do it in the order of the coordinates. You're going from x1 to x2. So you're moving in this kind of a way from x1 to x2. So the E, this E, it goes from P to Q, like from P to Q, from P to Q. So it goes like this. From P, sorry about that. It goes from P. So let me do that again very carefully. x1 is a smaller coordinate than x2, so you start at x1, you go to x2, and this side is that's what E is. So E starts at P and it finishes at Q. So you start at P and you finish at Q. I know it looks kind of strange why this one goes like that one goes like that, but ultimately it does not matter because the orientations are arbitrary. So you're going from P, you're going to Q. So so the terminal point is Q and the initial point is P. So as you can see, the terminal point, so for E, oh, I see what the issue is. Then they both, yeah, so then what happens here is they're actually both, so based on how we're doing it, it's actually both like this. So that's what we have for this matrix. And now we need the other matrix A. So the other matrix for A, this would be a matrix that's 3 columns that has to do with the 3 edges, E, F, and G, and you have U and L. So you have to find the boundary operators of those two, of these two. So you have to find the boundary of U. So let's go ahead and find the boundary of U. So the way we get the boundary of U is we're going to take the 0th face of U minus the first face of U plus the second face of U. That's how the boundary operator is defined, 0, 1, 2. So the 0th face of U is when we set x0 to be 0. When we set x0 to be 0, we're going from x1 to x2, and that's what we're calling E. Then boundary 1 of U, this is when we set x1 to be 0, and then we're going from, that's what we're calling from P to Q, right? That's what we're calling F, minus F. And boundary 2 of U, this is when we set x2 to be 0, so we're going from x0 to x1. That's the lower one, that's what we're calling G. So E, F, and G. So that would be, so the boundary of U, that 1, negative 1, 1. And now we do something similar with the lower map. So with the lower map is, so as you can see, this is actually trickier than using triangulations, but it's nice to do this. Like, it makes the calculations a lot nicer. But conceptually, it's trickier. With triangulations, there's less thinking involved. So I guess the price to pay here is you have to think more. So this lower mapping, it's from the, let's see, this is our simplex. So how do we define L? Well, the way we can define L is, let's say this is the one that's going along with G, this is the one that's going along with that one, and this is the one that's going along with that one. So when you find the boundary of L, what would that be? So you first set, so this is x0, x1, x2. So you first set x0 to be, and you get that one. So you're getting E, right? Oh, I'm sorry. So this is the one. Yeah, this is the one. This is E, right? So this is the one that's being mapped to. Yeah. So when you set x0 to be 0, you're going that way. So you're getting G. Then you do minus. So maybe I should write it out. So this is the 0 boundary minus the 1 boundary plus the 2 boundary. So the 0 boundary, that's when you set x0 to be 0, so you're getting just G. Then you have minus the 1 boundary. This is when set x1 to be, so in this case it's E, and this is F. So this is going to be, so G here, so E is -1, F is 1, and G is 1. Okay, so we got our matrices, and now you have to find the Smith normal form. Well, here's the way you find Smith normal form. It's basically just like row reduction. If you take this row and you add it to that row, then you get 0, 0, 0, 1, 1, 0. Right? You just basically add that in there. You just, maybe to write it, you take row 1, you add it to row 2, and then you substitute all of that into row 1. That's still not in diagonal form. The next thing you can do is, of course, you can swap two rows. You can do that because you're just interchanging the order of the bases. So that would be 1, 1, 0, 0, 0, 0, like that. And you can get rid of this 1. And the way you get rid of the 1 is you just take, because now you use column operations. So here you're going to take column 1, you're going to subtract from it column 1, column 2. You're going to subtract column 2 from column 1, and you're going to put that into column 2. So you would end up with 1, 0, 0, 0, 0, 0. Okay, so that's the Smith normal form for the A matrix. I'm sorry, for the B matrix. For the A matrix, when you do Smith norm, would be that if you were to add this one to that one, first row to second row, you would have 1, -1, 0, 0, 1, 1. Okay, and now if you add first row to second row, 1, -1, 0, 0, and then you would have 2, 2, 0, like that. Okay, and now you want to get rid of this 2, so you multiply the first row. Well, you basically, what we're doing is you're taking the first row, you add it into the third row, but you do it twice. So you would get 1, -1, 0, 0. Yeah, you multiply this by -2, you add it in, and you add it in, so you would get 0, 2, like this. Then you want to get rid of this. It's almost diagonal, so you can interchange these two. So you would have 1, -1, 0, 2, 0, 0. So this is the only number you have to get rid of. You're not allowed to divide by 2, by the way. So this is the only number you have to get rid of. So you would multiply, you would add this row to the, sorry, first column. You would take the first column and add it to the second column. And you would end up with 1, 0, 0, 0, 2, 0. So look at that. So this is the Smith normal form that we're getting for these matrices. So to summarize, we're going from 2 chains, and there's 2 of them, into 1 chains, there's 3 of them, and then we're going here by, again, and the matrices, the Smith normal form matrices is, this is the 3 by 2 one, which is 1, 0, 0, 2, 0, 0, and this is the one that's 1, 0, 0, 0, 0, 0. So now you can calculate, so this is, let's say, A, and that's B. So the kernel of B, well, as you can see, the condition is that the first coordinate has to be 0, and there's no condition on the other 2. So this is just isomorphic to Z2. That's the kernel. So to find the kernel mod the image, you would say that you have 2 z's, and you're going to mod out by z and 2z. So you'll have z mod 1z plus z mod 2z. And this is, of course, the trivial factor, and you're just left with z mod 2z. So there you go. And that right there would be the homology of the projective plane calculated by using this more general decomposition.